or graph, algebras, and graph monoids.
So very good morning to everyone, and I'd like to thank Professor Khan for inviting us here. Actually, I came to know about this gathering from Professor Rusbe. He told us in January when we visited him to New South Wales, to Western Sydney University, told us that there's going to be a gathering here, and so we wrote to you and thank you for inviting us. It's indeed a pleasure for us to be here. Yes. So some of the things that I'm going to do here today is an excerpt from what Professor Rusbe has talked many times in the Simpa schools. So if there is anything that you find any loopholes, you can just point it out. So I'm just going to give you an introduction to graph algebras. So what exactly are graph algebras? Graph algebras are algebras which are associated to directed graphs. Right? You have a graphs, say B. So the graph algebras are nothing but the algebras which are associated to directed graphs. So some of the classes of graph algebras are the C-star algebras, the graph C-star algebras, then the path algebras, the 11 path algebras, and there is something which I got to learn last year. It is known as Buhphang algebras. So this 11th path algebras you'll get to know from my student Rishabh. He's going to talk a bit about this. And I'd like to tell you a little bit about these Buhphang algebras. There is something which is a special case of Buhphang algebras, which are known as monomial algebras. So they are the algebras which are factoring. So if you take the algebra to be E, the graph to be E, then you take the algebra KE and you quotiented it out by an ideal, which is known as an admissible ideal. So we did a little bit of work here, and in the year 2024, we got a paper which is a note on injectivity of monomial algebras, which I got to work with my research scholar, and there's another professor from one Indian Institute of Technology, Kanpur. So this algebra, what it does is it deals mainly with finite graphs. So the graphs are finite. So one advantage of dealing with finite graphs is that the algebras associated with these graphs, they are finite dimensional. Over the underlying field. Secondly, the algebras, they are unital. And there is another result in this context of monomial algebras. It's a representation of algebras which states that every basic or that finitely generated, basic and connected, every finitely generated finite dimensional ring, finite dimensional, basic and connected associative algebra can be obtained as a monomial algebra or a Buhphang. Okay, so just don't worry about basic. Basic, it means that it is minimal. It is minimal, and connected, it means you cannot break it up further. So this is the the final stage. You cannot break it up further. Fall apart. So talking about algebras now. So algebras are rings. So if you look at if you have a ring R, suppose R is a ring, then in order to understand about this ring, so what ring theorists usually do is they take a bunch of algebras over the rings, so a bunch of modules. So those modules are projective modules. So they study the projective modules and then they understand the structure of the ring from the behavior of the modules. So now, if you take the projective modules over the ring, I hope you know what is the definition of projective module. A module is said to be projective if whenever you have an exact sequence, say m to n to 0, whenever this is exact, that and any homomorphism from here to here, say f, will be able to get a homomorphism in this direction. There exists a homomorphism in this direction. So now if you take two projective modules, P and Q, over the ring R, you take their sum, then it will turn out to be again a projective module. So and now if you take the iso classes of projective modules, then it forms a monoid. So I'm going to denote it in this way. VR, it is the set of projective classes of isomorphism classes of projective modules. So P is projective. Over R. So this will form a monoid. And the direct sum. So now talking about monoids, if you have a monoid, say the monoid of natural numbers, then it is possible to complete it to a group, can be completed to a group which is known as the group completion. So in this case, the group completion is, as we know, it is Z, which is obtained just by taking the inverses or the negatives of these natural numbers. But in a general case, if you take a module M, then corresponding to this M, there exists a universal group, which is denoted by GM, such that there is a homomorphism from M to GM. And whenever you have another group, say G prime, and a homomorphism from M to G prime, be shy, you'll be able to get a delta in this direction, such that when you compose these, you get the shy. Shy is the composition of these two. So,
Sorry. So
yes.
If it becomes you mentioned the notion of condition.
Right.
Large magnitude there, any topology space here.
Topology.
Yeah. Yes.
I don't think there is any topology here, because these are just monoids. Okay, so it can be any monoid. Well, you can also have monoids of topological groups. I'm not sure about that. Yeah, so far there is no topology in the general sense. So now how do you obtain this this group? How to form this group? So what we do is, on this product, on M cross M, we define a relation tilde by M1, M2 related to N1, N2, if there exists a K in M such that M1 plus N2 plus K is equal to N1 plus N2 plus K. So we can check that this is an equivalence relation, and a set of equivalence classes, the set of equivalence classes of this relation, M1, M2, this collection is denoted by this. So this is a monoid. M1 and 2 are in M. So yeah, so I think this is the, yeah. So this, you can form this. This is your GM actually. So this is a group. Okay. So what is the operation here? It is M1, M2 plus N1, N2. It is pointwise. So this M1 plus M2, M1 plus M2. And so this is a group. And this is the group completion of the monoid M. So when we take the ring R, so when we consider M to be the monoid VR, then what we get is this group G of M. It is called the Grothendieck group of this ring. So this is the group completion, which is known as the Grothendieck group. So I will stop here because from here, Rishabh will continue further to talk about the lipid path algebras.